Number 10. An Oxford philosopher published a mathematical argument in 2003 that concluded with unsettling logic that you are almost certainly not living in base reality. In 2003, philosopher Nick Bostrom at the University of Oxford published a paper in the journal Philosophical Quarterly titled, "Are You Living in a Computer Simulation?" The argument was not science fiction speculation. It was a formal probability argument built on a simple trilemma. Bostrom argued that at least one of three statements must be true. Either civilizations almost always go extinct before developing the technology to run detailed simulations of conscious minds, or advanced civilizations that do reach that technological level choose almost universally not to run such simulations, or, and this is the possibility that unsettled the academic world, the number of simulated conscious beings created by advanced civilizations vastly outnumbers the number of real, biological conscious beings that have ever existed. If that third statement is true, then any given conscious observer, including you, right now, reading this sentence, is statistically far more likely to be one of the simulated minds than one of the original, biological ones, simply because simulated minds would eventually vastly outnumber real ones. Bostrom has stated publicly, including in interviews given at Oxford's Future of Humanity Institute, which he founded and directed until 2024, that he personally assigns a meaningful, non-trivial probability to the idea that we are in fact living inside a simulation. This was not a fringe idea. It was published in a peer-reviewed academic journal, and it has been seriously engaged with by physicists, philosophers, and technologists ever since, including, most famously, Elon Musk, who cited Bostrom's argument directly in a 2016 interview at Code Conference, stating that the odds we are in base reality are, in his words, 1 in billions. Number 9. Physicists have discovered that space itself may not be smooth, but broken into tiny individual units, exactly like the pixels on a screen. In the early 20th century, physicist Max Planck, working in Berlin, derived a set of fundamental units now called Planck units, values built from the basic constants of physics, including the speed of light, gravity, and the reduced Planck constant. Among these is the Planck length, an almost inconceivably small distance of approximately 1.6 times 10 to the negative 35 meters. Many physicists, including researchers working in the field of loop quantum gravity, such as Carlo Rovelli at Aix-Marseille University in France, have proposed that the Planck length may represent an actual physical limit, the smallest unit space can be divided into, below which the very concept of distance stops making sense entirely. If this is correct, space is not smooth and infinitely divisible the way classical physics once assumed. It is granular, broken into discrete units, similar in principle to how a digital photograph, when magnified enough, dissolves from a smooth image into a fixed grid of individual pixels. A universe built from indivisible, discrete units of space is, structurally, indistinguishable from a universe rendered on a grid, precisely the kind of structure you would expect to find underlying a simulated reality running on a finite computational system, rather than a truly continuous, infinitely detailed physical universe. Number 8. The speed of light may not be a law of nature at all, but a processing limit built into the system running our universe. Since 1905, when Albert Einstein published his theory of special relativity, physicists have understood the speed of light, roughly 186,282 miles per second, as an absolute universal speed limit, a fixed constant baked into the geometry of spacetime itself. But some researchers exploring the intersection of physics and computer science have pointed out something strange about this limit. Every computer simulation, including the ones humans build today, requires a maximum processing speed, a limit on how quickly information can be calculated and updated across the system. If our universe operates on similar underlying principles, the speed of light would function exactly like a computational refresh rate, an upper boundary on how fast information, meaning matter, energy, and causality, can propagate through the simulation before the system would begin to lag or break down entirely. This idea has been discussed seriously by physicists including Silas Bean, whose broader research into simulated universes we will return to shortly. The unsettling implication is this: every law of physics that behaves as an absolute, unbreakable limit, the speed of light, the Planck length, the temperature of absolute zero, resembles, in structure, exactly the kind of hard-coded boundary condition a programmer would build into a simulation to prevent it from ever exceeding the computational resources available to run it. Number 7. A famous experiment first performed in 1801 appears to show that reality does not fully exist until something or someone actually looks at it. The double-slit experiment, first performed by physicist Thomas Young in 1801 and later refined dramatically through the 20th century using individual photons and electrons, remains one of the strangest, most reliably repeated results in all of physics. When individual particles are fired one at a time through two narrow slits toward a detector screen, and no one is measuring which slit each particle passes through, the particles behave like waves, creating an interference pattern, as though each particle passed through both slits simultaneously. But the moment scientists place a detector at the slits specifically to observe which path each particle takes, the interference pattern vanishes completely, and the particles behave exactly like solid, discrete objects, passing through only one slit at a time. This phenomenon, confirmed in countless experiments since, including detailed versions carried out at institutions like the University of Vienna under physicist Anton Zeilinger, who was awarded the Nobel Prize in Physics in 2022, partly for his work on quantum entanglement, suggests that reality at the smallest scales does not have a fixed, definite state until it is measured or observed. Some physicists have described this as the universe behaving like a video game that does not render distant terrain in full detail until a player's camera actually turns to look at it, calculating final results only when observation forces the system to resolve an outcome, rather than continuously tracking every possible detail of every particle at all times. Number 6. The fundamental constants of physics appear to be tuned with a level of precision that looks less like nature and more like deliberately chosen settings in a program. Physicists have long known that the fundamental constants of our universe, the strength of gravity, the mass of the electron, the value of the cosmological constant, sit at extraordinarily precise values, and that even small changes to any one of them would make a universe capable of forming stars, planets, or life completely impossible. Nobel laureate Steven Weinberg published research in Physical Review Letters in 1987 demonstrating just how narrow the acceptable range for the cosmological constant actually is, a value that, if altered by a fraction as small as 1 part in 10 to the 120th power, would have prevented galaxies from ever forming at all. There is no known physical law that requires these constants to fall within this narrow, life-permitting range. They simply do. Some physicists, when discussing this fine-tuning problem, have noted how closely it resembles a set of adjustable parameters, exactly the kind of configuration variables a programmer would input at the start of a simulation to define how that particular version of reality behaves. Numbers chosen deliberately, rather than numbers that emerged naturally from any deeper underlying necessity we have yet discovered. Number 5. There is a hard mathematical limit on how much information can exist in any region of space, and that limit behaves exactly like a storage capacity. In 1981, physicist Jacob Bekenstein, then at the Hebrew University of Jerusalem, published research establishing what is now called the Bekenstein bound, a formula proving that there is a maximum amount of information that can be contained within any finite region of space based on that region's size and energy content. This is not a limitation of our measuring instruments. It is a hard boundary built into the mathematics of physics itself, closely tied to the physics of black holes and the maximum entropy they can contain. The existence of a fixed, calculable information limit for any given volume of space is a deeply strange feature for a universe to have, if reality is simply continuous physical stuff extending infinitely in complexity and detail. It is, however, an entirely expected feature of a system built on finite computational storage, exactly the kind of hard information ceiling you would expect to find in a universe where every region of space is, in effect, allocated a fixed and limited amount of digital memory, a constraint no one has ever been able to fully explain through any framework other than physics, that behaves at its foundation remarkably like computation. Number 4. A physicist at the University of Maryland found what looked like literal computer error-correcting code hidden inside the deepest equations of theoretical physics. In 2010, physicist James Gates Jr. at the University of Maryland, while studying the mathematics underlying supersymmetry, a theoretical framework connected to string theory, discovered strange geometric structures called adinkras embedded within the equations describing the fundamental behavior of particles. While analyzing these structures, Gates noted, in public lectures and interviews, that the underlying code contained mathematical structures nearly identical to error-correcting codes, specifically a type called doubly even self-dual linear binary codes, the exact same category of code used in modern computer engineering to detect and automatically correct errors in digital data transmission, including in web browsers. Gates has been careful in his public statements to clarify that this discovery does not prove we live in a simulation, but he has also stated plainly plainly that finding computer error-correcting codes embedded in the fundamental equations that describe the building blocks of physical reality was, in his own words, the last thing he ever expected to find while doing pure theoretical physics. Error-correcting code exists in human technology for exactly one purpose: to preserve the integrity of information being transmitted or stored inside a computational system. Finding a structure serving that same mathematical function embedded inside the equations of particle physics is either an extraordinary coincidence or evidence that the universe itself is built using the same underlying architecture as the digital systems humans have only recently learned to construct. Number 3. Some of the world's leading theoretical physicists believe our entire three-dimensional universe might actually be a projection generated from information encoded on a flat, two-dimensional surface. In the early 1990s, physicists Gerard Hooft at Utrecht University and Leonard Susskind at Stanford University independently developed what became known as the holographic principle, a theory suggesting that all the information contained within a three-dimensional region of space can be fully described by information encoded on the two-dimensional boundary surrounding that region, similar to how a hologram encodes a full three-dimensional image onto a flat piece of film. This idea gained enormous credibility in 1997 when physicist Juan Maldacena, then at Harvard University, published a paper demonstrating a precise mathematical relationship, now called the AD-S or CFT correspondence, showing that a theory of gravity operating in a three-dimensional space could be mathematically equivalent to a theory without gravity operating on its two-dimensional boundary. In 2017, researchers led by Daniel Harlow at MIT continued building on this framework, showing deep structural connections between the holographic principle and quantum error-correcting codes, directly linking back to the exact kind of coding structures James Gates had already found. If the holographic principle accurately describes our universe, then the three-dimensional world you are experiencing right now, including your own body, is fundamentally a projection, a rendered output generated from a more fundamental layer of information encoded somewhere else entirely. A structure disturbingly similar to how a video game generates a fully explorable three-dimensional world from underlying two-dimensional data files stored deep inside a computer's memory. Number 2. A team of American physicists studying subatomic particles in 2012 found a strange directional pattern in cosmic rays that looks exactly like the fingerprint of an underlying computational grid. In 2012, physicists Silas Bean, Zora Davuti, and Martin Savage at the University of Washington published a paper in Physical Review Letters that began as an unrelated study of lattice quantum chromodynamics, a technique used to simulate subatomic particle behavior by modeling space as a three-dimensional computational grid. During this research, the team realized that if our own universe were actually built on a similar underlying lattice structure, there would be a specific, measurable signature left behind. The highest energy cosmic rays traveling through space, particles that approach a theoretical energy ceiling called the Greisen-Zatsepin-Kuzmin limit, should not travel through a truly continuous gridless universe uniformly in all directions. On a computational lattice, the highest energy particles would instead show a subtle directional bias, clustering preferentially along the axes of the underlying grid, a distortion that would never occur in space that is smooth and continuous all the way down. When Bean's team examined existing cosmic ray data at these extreme energy levels, they found a pattern of directional clustering consistent with exactly this kind of underlying lattice structure, a pattern the standard model of particle physics has never been able to fully explain through any known natural mechanism. The sample size remains small, and most physicists urge caution before drawing conclusions. But for the first time, a real, measurable physical signature, not a philosophical argument, not a thought experiment, but actual particle data, appeared consistent with the specific prediction that our universe might be running on a finite computational grid. Number 1. One of the most respected physicists at MIT has calculated, using the laws of physics themselves, exactly how many computations the entire universe has performed since it began. And the number is not infinite. In 2002, physicist Seth Lloyd, a professor at MIT specializing in quantum computation, published a paper in the journal Physical Review Letters, calculating the total number of elementary computational operations the observable universe could have performed since the Big Bang, based on its total mass, energy, and age. His calculation placed the number at approximately 10 to the 120th power operations, an unimaginably large, but ultimately finite figure. Lloyd's underlying argument, expanded further in his 2006 book Programming the Universe, is not that the universe was necessarily built by an external intelligence running a simulation, but that the universe itself may be, at its most fundamental level, indistinguishable from a giant quantum computer, a physical system whose fundamental behavior is computation, constantly processing and updating its own state according to the laws of physics, in exactly the same way a computer processes information according to its programming. This idea that the universe is not merely described by mathematics, but is, in its physical operation, an act of computation, connects directly back to everything discussed throughout this list. The pixelated structure of space at the Planck length, the processing limit of the speed of light, the finite information capacity described by the Bekenstein bound, the error-correcting code hidden inside the equations of particle physics, the holographic projection of three-dimensional reality from a flatter, more fundamental layer of information, and the directional fingerprint of a computational grid detected in the very cosmic rays reaching Earth from across the universe. None of this proves, with final certainty, that reality is a simulation, but taken together, it means that the universe, examined closely enough, at every single level physicists have been able to test, behaves exactly like a system running on finite, structured, computational rules, and no one, not Bostrom, not Lloyd, not Gates, not any physicist alive today, has been able to fully explain why that would be true of a universe that was not, in some fundamental sense, being computed at all. If you want to see more videos like this, click the video on screen now and make sure to subscribe.